And as an introduction to the geometry session, I would like to cover with you, in brief, the Cartesian Coordinate System in 2D plane as the first stage. And what we see here, we see basically a 2D plane having an x-axis and a y-axis. And just for the sake of the introduction, we marked here several points. And we can see here that in green, the point in green is where y equal 3 and x equal 2 on a positive quarter of the picture. The negative x and the positive y has a red point in there, -3 and 1. -3 is the x on the negative side of it, and 1 is positive in the upper side of the y-axis. Same idea with the -1.5 and the -2.5. It's the blue point, and the blue dot in this particular plane. It tells us that we are in the negative quarter of the plane of the 2D plane itself, but that's how we express points in a 2D plane. Please note in purple that the origin of this plane is where x and y both 0. That's what we call the 0, 0 point, the origin. So in just a couple of minutes, we just covered the basic of the 2D Cartesian coordinates. And if we look at the circle, for example, still the very basic of Cartesian coordinate system in a 2D plane, we have a circle, and in this particular example, radius of 2. Its center at the origin marked in red, and the equation is x minus a in the power of 2 plus y minus b to the power of 2 equal r to the power of 2, where a and b are the coordinates of the center AB and r is the radius. This is the basic Cartesian coordinate system when we talk about circles. When we move to 3D Cartesian coordinate system, then there is a z-axis that participate into this so-called game. We can see the y-axis is the vertical one, and there's a scale. The x-axis is the horizontal one, and the z-axis is the depth. And if we want to express a point in space, we should express it in these three items, x, y, and z. X, y, and z is, in this particular case, 90, 80, 50. We always actually start from left to right, x, y, z, meaning 90, 80, 50. So x is 90, y is 80, z is 50. That's in 3D. Let's apply these last three slides into robotics. And in robotics, we start talking about degrees of freedom. The picture on the left demonstrates kind of clearly the 6 degrees of freedom, which are most typical to articulated robot. We've covered articulated robot in previous sessions, but here we can see that there is a 1 degree of freedom in blue, in dark blue, covering the rotation and the going up and down of the joints of the robot itself. In red, we have back and forward, which is another degree of freedom. Yellow is right and left. And then comes roll, pitch, and yaw. And roll, pitch, and yaw are associated with the gripper, with the end effector, with the end manipulator. By the way, these three names are equivalent: gripper, end effector, and manipulator. So when we'll talk about one of the three, you will understand that we're talking about that end part that has a roll, has a pitch, and has a yaw. And let's take this 3D Cartesian coordinate system that we just learned a couple of slides ago and apply it to robotics. And the robots is basically consist of nodes. Each node has a 3-axis, has its own 3-axis. The base node, x1, y1, z1, is the one that rotates and moves the entire robot. Going up to part number 1, we will learn about it later in depth, but we can see that every single segment of the robot has its own 3 dimensions, has its own ability to move in each of these directions. It constitutes 6 different degrees of freedom. So when we count the number of joints, we will see again that this is a 6 degree of freedom articulated robot. And that's what it is. We're talking about geometry. Let's look at this a little bit more in depth. The picture on the left. R-1 is an external home. The robot needs to have two homes. One of them is externally, one of them is internal to the robot itself. External home is a point, a reference, what you call 0, 0, 0, from where the position of the robot is being measured. So the robot working in space, we as a planners will know exactly where the robot is in our environment. So if we have a production line or assembly line in a factory and the robot is doing pick and place, that external home can be some point at the beginning of the conveyor or the beginning of the assembly desk, assembly platform. And that home, external home, is fixed no matter if we move the robot in the working place. Then we have the internal home of the robot, which is in the base. No matter where the robot is, that home, this personal home of the robot, remains the same, and from which all the joints are calculated. The position in space of all the joints are calculated. So the external home is to know exactly where the robot is within its environment, and the internal home is to know where each joint of the robot is within the robot working space, operating space. We still on the picture on the left, every single joint, as we said before, has 3 different axes. And these 3 different axes are influenced by some external physical forces, one of which is a torque. And that particular torque is being measured compared to 2 different homes. Torque as compared with the internal personal base of the robot, in order to assure that when the robot moves, go from one point in space to another point in space, the torque associated with it is within its technical specification. And the torque associated with the external home is to know, since external home is relevant to the environment where which the robot is operating at. So when we move the torque from one position in the environment to another position in the environment, we don't hit any other obstacle that is within the global, let's say, working environment. Please note that there's a gripper at the end. We're still on the picture on the left. There's a gripper on the end, and the gripper basically has 2 sets of XYZ coordinates. Number 1 is the actuators of the gripper itself, and then there is the fingers of the gripper. And the reason that we have 2 sets of XYZ coordinates, one of them is the actuator of the gripper and the other one is the fingers of the gripper, is because within these fingers an object will be held. And that particular object has its own physical characteristics, which will change the behavior of the fingers, will change the behavior of the center of gravity, will change the torque associated with the gripper itself. So first of all is the source of the gripper, XYZ, and then there is the tip of the gripper has its own XYZ because of that particular object that it's holding. The picture on the right is what we call, it's an articulated robot, can look at this as also a scalar robot, has its own set of XYZ, also a rotation. We can see in joint number I, joint I basically is only a turning. It does have an XYZ coordinate, but all what it does, it turns. And please note that on the picture on the right, the end calls link I-1. In every set of joints, we have to determine which is the reference joint, where we actually start counting the joints. So we select a joint, call it a reference joint. Everything closer to the base of the robot is link -1, link -2, link -3. Everything that will be towards the gripper of the robot will be link +1, link +2, link +3. So here we demonstrated quite clearly the joint I is the joint in the middle. As we get closer to the base, we call it I -1. Closer to the gripper, we call it joint I +1. And same thing with its own coordinates. X, I +1, Y, I +1, Z, Y +1, etc., etc. And let's look how we actually define an angle. When we tell the robots to move from X, Y, Z, X1, Y1, Z1, point 1 in space, to point 2 in space, and when we do a rotation or just a move, basically we change the angles of every single link, no matter if it's the link minus or the link plus. And the way we express the angles is 1 relative to axis J1, J2, J3, and we can see it quite clearly that theta 1 is related, there is an angle between I1 and the x-axis, and theta number 2 is related, is the angle between I1 and I2. I'm sorry, J1 and J2. And theta number 3 is between J2 and J3, etc., etc. So we express the degrees of freedom and the angles of rotation of a particular link based and reference on the previous link. This is something very, very, very important. The picture on the right demonstrates a kind of as an example, numerical example, where we have theta 1 is 39 degrees between the vertical axis J1 and the next link, which is J2, and then the y is 75 degrees between J2 and J3, and the z is 51 degrees between J3 and J4. So the angle of the beginning of the gripper, the actuator gripper, relative to x-axis is x plus y plus z equal 165 degrees in this particular example. And this is somewhat slight different relation of how we define the angle. Look at the point on the left part of the picture. We see the point where the gripper is, which is x, y, and theta. And the angle theta of the starting position of the gripper itself is alpha. And alpha is basically theta 1 minus beta. All these angles are in order to help us define the position of the gripper prior to begin doing the roll or the pitch or the yaw. So we have to move the robot to a particular point where the gripper will be. When we will get there, the operation will start. But in order to get there, I have to find alpha. In order to find alpha, I have to move the links and the joints of the robot in order to create beta. And alpha plus beta equal theta 1. Again, just an example on the right hand side. We have the links, we have degrees, and we can actually determine exactly the position of the actuators of the gripper in space. And we talked about the joints, we talked about the links, and here is another example. Of articulated robot. But in this particular slide, I want to pay your attention specifically to the fact that each joint, one axis of it, is along the axis of the previous link. And the red elliptical sketch over there on the left-hand side demonstrated quite clearly. Look at the red arrow as it continues along the path of the previous link, the one closer to the base. So every single joint, which basically connects two links together, one specific axis is parallel to the XYZ of the previous link. And in this particular case, we can see the maximum robot operational radius. It's the maximum how far that the robot can actually operate. Later on in the seminar, we will discuss in depth the problems associated with working at the end, at the edge of the working envelope. Torques, vibrations, stability, reliability, repeatability, all these parameters we will cover, but when we have a situation of this, when the robot is extend fully to the end, to the edge of the working environment, it's problematic. It's problematic in the sense that it's hard to predict the quality of operation that will be in the endpoint. So this is why we will try to work not at the far end of the working envelope. We will cover that much later. Segments. We talked about links, we talked about joints of a robot, but first of all, let's understand that every single link has two joints in its end. And the two joints are connected to another link, which is basically is being held from both sides with two joints. So each module contains one link and two nodes. The joints can be called nodes as well, except for the gripper. The gripper is the end manipulator, end effector. It means that it has three axes, X, Y, Z, can do, like we said, roll, pitch, and yaw, but it does not have a joint behind it. Beyond that, it does not have a joint. So there's one particular point in the structure, and the entire gripper is basically fixed, mechanically fixed to a one point. That means that if we isolate the gripper itself, and from the entire robot, the center of gravity of the gripper itself, even without holding any object, is away from the joint, its own joint, which might create some problems, especially if we'd like to do a pick and place of heavy object. Not only that without an object, the center of gravity is outside the holding point from a mechanical point of view, but when we add the weight and torque, acceleration and deacceleration, and inertia of the object that the gripper moves, we even increase the problem of having a center of gravity away from it. And there are two ways to describe degrees of freedom. One way, on the left-hand side, is having the length of the link and the angle of rotation of that particular link. That's one way of describing it. We can go from link to link and calculate and determine the amount of degrees that that particular link moves from initial position to the next position. Next position becomes initial towards the next one. So the initial position and its angle goes to a second position and its angle. That's one way to describe a degree of freedom. Another way to describe degree of freedom on the right-hand side of the picture is having X, Y, Z coordinates values for each joint. Knowing that, we will know where each joint is in space in our working envelope. And we can define the degrees of freedom according to this position in space of joint number 1 and position in space of joint number 2. So there are two ways. And when we plan an operation, any industrial process using a robot, we basically convert the robot to a skeleton drawing. And this is the first time in our seminar that we look at the skeleton of a robot. And the skeleton of a robot is basically a presentation, a line presentation of the mechanical structure of the robot in such a way that we will know the length of each section, we will know which axes operate on the joint at the end of the link, and we basically present the robot. And we actually, when we look at this, we actually see a robot. It's only in a line presentation. We call it skeleton. And every single joint has its own coordinates. We know exactly the initial position in space when the robot is at home and when the robot is in an initial position prior to starting the operation. And when we need to create a task of going from one point to another and another and another in space and doing operations in each particular thing, basically we have to draw set of skeletons. And in each position of the robot for each task, we will draw a specific personal skeleton. So that particular skeleton that we see right now, meaning that the end point, the gripper, is in a particular position. If we need to move the end point to another position, obviously we will have a different skeleton. Same robot, same process, but because different positions of the gripper, each position will have its own skeleton. So we can understand that in order to operate a complete process, and in this process, there are 20 positions and locations of the grippers. There will be 20 skeleton drawings to the process. A skeleton basically is a 2D type of presentation, a line presentation, as we said before. In the picture on the right, we can clearly see how we convert the three-dimensional picture of the robot into its own skeleton. This line presentation of skeleton is still on the right-hand side of the picture. If we look at it and compare it one-to-one with the robot up there, we see that they actually look alike. But that's only for a very specific position in space, in the working envelope of the end manipulator. Each joint has its own three axes. We can actually count the number of degrees of freedom, and in this particular one, there are 5 degrees of freedom, not including the base of the robot itself. The picture on the left, on the top, we see the arm of the robot and the three-dimensional type of presentation of the line presentation. The 3D line presentation on the left is different than the 2D line presentation on the right-hand side, in the sense that the z-axis gets into operation, we kind of get a better feel of where the robot is at any given point of time. So when we do skeleton drawings as part of the path planning and the task planning of the robot, sometimes we move from a 2D line presentation to a 3D line presentation in order to make sure that we do not have collisions. The 3D line presentation gives us the picture where the 2D does not give us the picture where we might have a collision. Collision with another robot, collision with the object that we want to work on, pick or place. That's very, very important. Converting the 2D line presentation to the 3D line presentation when we go from 1 degree of planning to the 2nd degree of planning, going more in-depth planning of the path.